Hi everyone, this is Jim Corkins, and we are now in the next part of electric fields. We're going to be doing electric fields in one dimension, and we're going to do more about the calculations and quantifications of it. Okay? If you haven't done the reading, please do so. Those readings are very helpful for this. It gives you a different perspective than the one I'm teaching, slightly different perspective. And they're actually pretty good books. The OpenStax books and the Survey book, they're both quite good. All right, so just to remind you, we're going to be doing calculations of electric fields due to point charges. So again, you put a sensor here in outer space, not a charge, an electric field sensor, and you're detecting the electric field vector at this point. And so you'll put the sensor there. This is a positive charge, the distance r away. We put an electric field sensor here. It's going to be pointing away from it. And how you calculate it will be kq divided by r squared. So this electric field will be pointed to the right. And it'll be pointed up. Okay. And if this is angle theta, it'll be E cosine of theta pointed in the positive x direction. And the electric field here will be pointed in the positive y direction, and that'll be E sine of theta. And that's in the y direction. So it'll have two components in this case. So the approach that you're going to be doing is very similar. It's the same approach that you'll be doing when you're calculating forces, except now we're not dealing with the force on a charge. We're just dealing at what is the electric field at this point in outer space. Now, let's practice this, and then we'll go into the formal procedure for calculations, and then we'll do some practice problems, which will be part of your tutorial. Okay? So you've done this before, but with forces. So here, just say you've done this before where you're going to place, you have two positive charges here, anchored in place and can't move on this number line, and you're going to place a third positive charge somewhere on this number line that is free to move, but where you place it, it won't move, meaning the forces will be balanced and there'll be no acceleration vector. Well, in this case, you're not placing a third charge that's free to move. You just want to know where the electric field is going to be zero. Okay? So, where will the electric field be closest to zero? Will it be at 1, 2, 3, 4, or 5? So take a moment and just guess where the electric field is likely to be closest to zero. Okay? Pause the video now. All right, so if you look right here, let's look at the electric field vector, and I'm going to call this guy over here the purple the purple positive charge, and this is the red positive charge. Since you're really close to the red positive charge, its electric field is going to be pointed away from it and will be large. And the purple's positive electric field vector is going to be pointed away from it, but it won't be very big. So when you add those two vectors together, you've got this vector plus a purple vector. Well, the overall electric field at this point will be this big. So it will be pointed to the left. So obviously the electric field is not zero. You would have the opposite of this over here at number 5. So likely you guessed number 3. So at 3, the purple vector, you're going to be closer. That's right on here. So at 3, you're going to have an electric field vector pointed to the left, away from the purple positive 1 Q charge. And you're going to have the red positive 1 Coulomb charge. It's going to be pointed away from that guy. And when you add those two vectors together, it doesn't matter the order at which you do it, the red charge, and then you have the purple charge. You're aligning them tip to tail. So the tip of the red charge is the tail of the purple charge, is electric field. Well, you started and ended at the same place. So the electric field is 0. Right there. Okay? And we could look at this in our little simulation. So if you get a positive 4 Coulomb charge, and we're going to place it right here. I'm going to do my best to put it right on top of that. And then we get the same positive 4 Coulomb, microcoulomb charge. 1, 2, 3. 1, 2, 3. I'm going to put it right here at the center. If you look at the electric field vectors at this point, notice it's pointing away from that one, pointing away from that one, but in the center, it's hard for me to click right there, but that vector is basically 0. I must have clicked a little bit off the center. Okay, so you could check with this simulation. Incidentally, going back to this, since we had learned that force is equal to Q1 KQ2 over R squared, and now we know that that Q1 is being multiplied by the electric field Q2. Well, if you placed a Q1 right here, you're going to place a Q1 right at that center part. Well, that force acting on that positive Q1 times that electric field that is 0, well, that's just going to be 0. So the reason why when we did this exercise before with forces, the Q1 had no net force on it, and thus had no acceleration on it, because the sum of forces is 0, is because the overall net electric field at that point was 0. Okay? So that's another perspective. So the net electric field at 3 is 0. So you place a charge on that 0 electric field, well, now your force is 0. Okay? Let's go through this. Where on this number line, or closest to, will the electric field be closest to 0? Okay, you've got a negative 1 Coulomb charge anchored in place, negative 2 Coulomb charge anchored in place. About which number will the electric field be closest to 0? Pause the video now. Okay, let's start on the outside. I'm going to start right here. Actually, start at the center. Do it a little bit differently. So this is now going to be the purple charge, which is the 2 Coulomb charge. The 1 Coulomb charge is going to be blue. So you place the sensor right here at the center. The electric field is going to be large. The purple 2 Coulomb charge is going to have an electric field that is going to be large and pointed towards it, but half as large and pointing towards the negative 1 Coulomb charge. So when you add those two fields together, walk to the right this far, and then add that vector, that blue vector, to that. The overall net electric field, if you started here, you walk to the right 2 steps, walk to the left 1 step, your net electric field will be this big. So this will be the net electric field vector. Okay. If you put the sensor over here, well, now you're really close to that negative 1 Coulomb charge. So your electric field vector is going to be large and pointed to the right. Let's try that again. Large and pointed to the right. And the purple -2 Coulomb charge will be smaller. And then when you add those two vectors together, you just get an overall net electric field that is pointing to the right. So you started here, you walk to the right a bunch of steps, walk to the right even more. So you ended right here. So start to finish, the overall net electric field at this point would be large and pointed to the right. Okay? Now, I think we're going, if you remember, if you put it here, if you put a positive 1 Coulomb charge right here at 2, it wouldn't move. And that is because at 2, I'm going to move those vectors up. Okay, hold on a second. Sorry about that. I had to do some landscaping there. So if you put a field sensor there, well, that field sensor is going to have electric field pointed towards that -1 Coulomb charge, which will be large, which I'll use down here. And it'll be large due to that positive, that other -2 Coulomb charge. So here is where the electric field is equal to 0. And so if you place a charge at that point, like a positive 1 Coulomb charge, well, the force is going to be a positive 1 Coulomb times an electric field of 0, which is the net force is going to be 0. Okay? So we could go to our handy dandy simulation and refresh this, and we'll see what we have here. I'm going to go ahead and place, and those were negatives, so I'm going to place, let's say, actually, -8 Coulomb charge right here. Big one was over there. And then -2 Coulomb charge, 2, 3. And so, if we put field vectors here, like in the center here, notice the electric field is pointed to the right. Over here, the electric field will also be pointed to the right. But if you get close, trying to find it, right about here, that's where the electric field is 0. So I wish you could redo this, but so right here, you'll notice those little lines are just arrows. So going back to this, that's about here. It's actually in between 2 and 3, but closer to 2. All right, last one of these, and then we'll move on to actually doing some of your tutorial problems, or setting you up to do the tutorial problems. All right. So here we have a positive 1 Coulomb charge, and we have a -2 Coulomb charge. Where do you think the electric field is going to be equal to 0? Pause the video now. Okay, well, I'm going to start off. And I'm going to place the sensor right here at 3. The positive 1 Coulomb charge is going to be pointed to the right, like this. And the -2 Coulomb charge is going to be pointed also towards the right because it's negative, twice as large. In fact, the electric field is not going to be 0 anywhere in between these two charges. Where it will be 0 is right here at 1, or closest to 1. you'll have an electric field pointed away from that positive 1 coulomb charge, and then an electric field pointed towards the negative 1 coulomb charge. And so there is where the electric field is going to be equal to 0. And again, if you place a Q1 on top of that, where that electric field is going to be 0, you'll get 0 force acting on it. Okay, and so let's refresh this, and you'll see that this is really at a far distance. So, and we'll put like a negative 4 coulomb charge right here. And so if we start playing with the field vectors at this point, yeah, so it's about 0 right in this range, right in here. So definitely closer to the positive 1 coulomb charge. Now, if we go in the center of this, notice the electric field is just pointed to the right no matter where you place it. Okay, and here it'll always be pointed to the left. So, okay. Oops. So that is where the electric field will be closest to 0. All right. And so in doing that, you're kind of qualitatively understanding the addition of electric field vectors and how the further away you are, the electric field is going to drop off, and how more charge will mean a larger electric field vector. Okay. So this is the procedure that we're going to go through, which is the same thing as forces, really, except we're just looking at electric fields and we're thinking about a sensor and not placing a Q. So let's do this, and I'll talk about the procedure that that we're going to follow for solving all electric field problems due to point sources. Okay. So this is your tutorial. Okay. So this is the tutorial for 2.1, and it's in 1D electric field vectors. All right. Your first 2 pages are represented like this. Oops. So I noticed there was a positive Q there. It should look like this. That little dot, that's supposed to represent the sensor. Okay. So in this case, you're for page number 1, you're supposed to basically create an equation for the electric field as well as the direction of the electric field at this dot. Okay, so this is the very first one. So here's what we're going to do. Okay, the first thing that we're going to do is lay down a coordinate system. Okay, and I think it might be easier. Well, I'm going to do it off to the side here. We're going to lay down a coordinate system. Even though this is in 1 dimension, we're still going to label this positive x, positive y, negative x, and negative y. All right. Now, what we're going to be doing, should be a little bit bigger, is this red charge is creating an electric field on this sensor. So it's creating an electric field on this sensor. So it's going to be pointed away from that positive 2Q charge in all directions. So now that vector is pointed to the right. This is the electric field. And we're going to label this electric field vector just like we did in forces. What is causing it is a positive 2Q, and it's a distance d away. All right. So we're labeling it just the same way that we did. Normally, we would put like a positive 1Q here in the center, and that would help us construct our force equation. But since there is no charge at this sensor, it's just, where is the sensor placed? So this is going to translate what we have done in electric forces, or the Coulomb force section, is going to help you out greatly here. So here we're summing the electric field vectors. You always add electric field vectors. And summing the electric fields, we only have one electric field vector, which is labeled this way. So these subscripts that we wrote is actually telling us our equation. So this equation, so this is going to be pointed to the right, so positive. We have absolute value. This is just going to be K, and that's times a positive 2Q. So I'm looking at the subscripts when I create this. And it's a distance 1D away. Don't forget the brackets around that. And multiplying this all out, what we're going to get is a positive 2KQ squared divided by D squared. So the answer for your very first part is going to be positive 2. Okay. And I think in the instructions, I'll tell you to round to a certain point, like to the hundredths. So I believe, let me check. Let me do something real quick. Yes, so we're going to round to the hundredth. So your first answer is going to be positive 2.00. Okay. That's the very first one. That's the very first page. The second page here is we have a sensor right here. Okay. And now we're going to go ahead and we're going to look at the electric field at that sensor. So I'm going to put I'm going to put our little coordinate system. Label it just like we did before. Negative X and negative Y. Now the blue charge is closer, so its electric field is going to be larger and pointed to the left. So it's pointed to the left. That electric field is due to a negative 1Q, and it's a distance D away. The positive 1Q charge is further away, and positive charge's electric field is pointed away from it in all directions. So it'll be pointed to the right, and it's a positive 1Q, and it's a distance 2D away. All right. Now we're going to sum our electric fields in the X direction. I should put an X there. Don't sum the electric fields in the Y direction on this one, because that is just going to be 0. Now, let's skip steps, just like we were starting to do in forces. So I'm going to go right to constructing the equation. Okay? So starting on the left, copy that negative in the front, absolute value, K times, I'm just looking at the subscripts, negative 1Q, all over a distance 1D away, squared. This is going to be plus K times a positive 1Q, and this is a distance 2D that we're going to square. Okay, multiplying all this out, we're going to copy this negative down. K times 1Q over 1D, so this will be KQ squared, nope, just Q divided by D. I put a square up here. Why, Jim? Why? Just caught myself. There we go. Just programmed to do forces. So this is like a negative 1KQ. This red guy is going to be a positive, and that's going to be KQ over 4D squared. So when we're going to pull out a KQ over D squared, and this is going to be negative 1 plus 1/4. So this is going to be kq over d squared, and this is going to be, what is that, times a positive 3/4. So your answer here will be positive 0.75. Okay. In the tutorial quiz, you're going to have to put in decimal places. So we're going to do the 100th on that. So there you go. There's the first 2 pages. All right. There is a third page. It looks like this. And I'm doing this because it helps you out. And this, and here, we're going to go ahead and do this all at once. I think you have 2 of them that you're supposed to do. So we're going to go ahead and do the electric field vectors here. All right. This positive 7q is creating an electric field pointing up and away from it. Okay. The negative 2q is, and that is going to be positive y direction, so that's going to be positive 7q, and it's a distance d away. This guy, the negative 2q, the electric field is going to be pointed towards it. It's going to be smaller. So this can be, that vector is pointing down, and this is due to the negative 2q, and it's a distance 1, 2, 3 d's away. So when you sum the electric field here, so this one you could kind of skip the formal coordinate system if you want. It's supposed to be a real quick diagram. You don't have to get too crazy with it. You can just do it like this. And then, like I taught you, go right to the equation. So starting from up, we got positive, and this is going to be k times 7q all over a distance d away that we're going to square, minus k times a negative 2q all over a distance 3d that we're going to square away, so that red guy is going to be positive 7kq over d squared, and the blue guy is going to be, what is that? 2 over 9 kq over d squared. So this answer, 7 minus 2/9, so that's going to be 6 and 7/9 kq over d squared. Okay. And whatever, and that's going to be positive. I should put the positive there. So this is going to be positive. 7 divided by 9 equals plus 6, so that's going to be 6.78. So this guy is going to be 6.78 kq over d squared. So this answer is going to be positive 6.78. Okay. So I'm going to go through these other ones quickly. The red charge is creating an electric field pointed straight down. So that's going to be negative. Positive 7q, that is distance d away. This guy is going to be pointed also down. And that's going to be negative 2q, comma d. And I'm just going to go through all of these. This guy's electric field is, so the red guy's electric field is going to be getting smaller. And that's going to be negative E plus 7q. That is distance 1, 2, 3 Ds away. And here it's going to be a little bit smaller. Negative, positive 7q, and it's a distance 4d away. When you're doing these, I want you to be smart about how you're doing it. And I should have made this vector the same size. You don't have to be as detailed as me. Just two down vectors would be fine. So this electric field is going to be pointed up, and it'll be negative 2q, and its distance d away. And here it'll be a little bit smaller, and positive 2q, and its distance 1, 2 Ds away, right? So when we do our calculations, we kind of have it all set up. And let's do this first one. Try to do it as quickly as I can. So this guy's electric field, well actually I'll start with red first since I did that up here. So negative, and you have a k times a positive 7q all over a distance d away that we're going to square. The negative charge is its electric field is also pointing down, negative 2q, and its distance d away, so that's going to square that. And when we bring this out, you don't have to do every single step, but this is going to be 7kq over d squared, and this is going to be negative 2kq over d squared. And so the answer here is going to be negative 9kq over d squared. So the answer to this is going to be negative 9.00. Okay, let's sum the electric field here, and they should be in the y direction. Okay, and starting with red first, negative. And I'm just looking again at the subscripts. And that's 3D that we're going to square. That blue charge, its electric field is now pointing up. Distance d away. So this guy right here is going to be 7 over 9 kq over d squared, right? 7, 3 squared, yep, 9. And then we're going to go plus 2 kq over d squared. So the answer to this one is going to be positive 1 and 2 ninths kq over d squared. So whatever 2 over 9 is, 2 divided by 9. So that's 0.222. So adding 1 to that. So this is, that should be black ink. positive 1 and 2 ninths KQ over D squared. So that's going to be positive 1.22 KQ over D squared. So positive 1.22. All right. Last one. Starting with red first, it's pointing down. And that's K times positive 7Q all over a distance 4D away that we're going to square. Make sure that looks like a Q. Plus K times a negative 2Q all over a distance 2D away. So this one's going to have some fractions here. So this first one is going to be negative 7 over 4 squared. So this is going to be negative 7/16 KQ squared, KQ over D squared. I want to put a Q squared there. This next one is going to be positive, and that's 2 over 4, so that's going to be 1/2 KQ squared. See, I want to do that over D squared. So this one I'm just going to put in the, so this is going to work out to be plus. So 7/16, 7 divided by 16 equals, we're going to make that negative, plus 0.5. So 0.06, I'm going to round, 0.06 KQ over D squared. So this is positive 0.06. Now, what I'm going to have you do in this is a 9.00, is I'm going to have you organize these from largest to smallest. So, as in magnitude. So we're going to take the magnitude of this and organize them from largest to smallest. Forget about the sign or the direction of the vector. So EB's is, that magnitude is 9. That's going to come first. Then EA, that magnitude is going to come next. Then EC, that magnitude is going to come next. And then ED, that magnitude is going to come next. Okay, so in this last page, while you'll have to write your answers down so you have a numerical answer, you're going to have to organize them from strongest electric field to weakest electric field, just the magnitude. Okay, well, that is the lead-in. So that is lecture 2.1, but it's also for the lecture tutorial, creating electric field equations. All right. I hope you have a wonderful day. Thank you.